Üdvözlök mindenkit, aki nem ismerne, annak bemutatkozok. Zsombor vagyok, a Gillemot László Szakkollégium elnöke, és itt mellettem László látható, aki az AFT-Hungary Kft-nek a rétságüzemének a mérnökségét vezeti. Ugye itt az AFT-nél a MIM, vagyis a Injection Molding, vagy magyar nyelven fordítva a fémfröccsöntés technológiájára foglalkoznak, és nem is rabolnám tovább a szót, továbbiakban angolul fog előadni. Piacra az érthetőség szempontjából magyarul lesz, de tévesztem is.
Good evening, my name is Alan Bird. I'm the engineering manager over at AFT. This evening we're going to be talking to you a little bit about MIM and metal injection molding, and we're going to do what's kind of known as a mini MIM school. And so I know some of you have been up to RACHAG, and we want to show you what our technology is and how it works, and we can introduce you to here at the school. Yes, I will be speaking in English. However, the slides are going to be in Hungarian for better understanding. So, our technology is a combination of three factors. You want complex geometry, 3 dimensions. Okay? If it's 2 dimensions, other technologies like stamping or screw machine work. A relatively large volume. We like to look at 10,000 pieces a year and up, 50,000, 100,000, and in some cases we deal in the millions. So generally for us, the more the better, not just for us, for the technology. So you want volume, complex geometry, and then the right size. It says the right algebra. About, let's say maybe a golf ball size, in the smaller range. Some of the bigger technologies like investment castings, they go for big like seat casings and things like that. Ours is a little bit smaller, but more complex, and for steel and stainless steel. And that's how you get the combination of these technologies. Plastic injection molding and powder metallurgy. You get the shaping, the complex geometry and formability of plastic injection molding, and also you get the strength of metal. So you get some really complex and neat shapes that usually you don't get with metal. So what do we call the MIM? What do we call the MIM process? So over here at this stage, we call this our compounding, where we make we make the material. And up at AFT and RACHAG and other places, we make our own feedstock, what goes into the injection molding machine. So we buy metal powder, and then we have a process where we put that together with plastic binders, wax, polypropylene. It's like making a cake. Flour and sugar, and you put them together, and then we have a mixer. And it's kind of an oil heated mixer, and that's kind of like the baking process. And once that's done, you have a material, and we grind it up, and it's just like plastic injection molding. You can see it. It's granules, and then these granules, once they're compounded, they go straight into. You can see they go straight into the injection molding machine. So these are called the green parts, and that terminology comes out of the powder metal industry. You have the green parts. It's not green, and if you're familiar with plastic injection molding, I mean, you have class on it or a semester on it. That's where you get the formability. The machine is plastic injection molding. The molds are plastic injection molding. So we can use that technology. It's a very common technology to get those shapes that you otherwise would not get with either powder metallurgy or castings. Then the next step is Kutanya, Kovanish, we call it the debind removal. So now that you've formed your shape with your plastics and your powder, you want to remove that binder. So you don't want it's done its job, you don't need it anymore. So you want to use this, and for us, it's a solvent debind bath. Usually lasts about maybe 6 to 8 hours. And as it sits in that bath, it extracts the binder. If you extracted all of it, it would go down to its powder form. But it's very difficult to actually do it. You'd have to leave it in the bath 3 days. However, you can not extract enough, and then when it gets to the sintering furnace, it can actually explode a little bit. So we want to make sure we have enough debound happening. And occasionally we do see that, so we have to adjust our process. And then, what the main one is sintering, and that's where it becomes the full-on, fully dense, 100% metal part. And this is where it's experiencing the shrink. And I can show you that. So we usually get between 15 to 25% shrink. And that's actually, when we show people in the plastics or the powder metal industry, they're like, wow, that's a lot of shrink. They're used to 2 or 3% shrink, not 20% shrink. So that's actually a big value for shrink when you put it through the sintering process. Sintering process, we'll get to the details, but that takes about 24 to 28 hours from close the door and start to open the door and pull the parts out. And it goes up close to the melting temperatures of metal and steel within about 50 degrees centigrade, but it doesn't get it. And that allows it to come to the uniform dimensions of the part. Some of these slides, everything, you can just see we have 3 locations. One in Florida, we mainly do medical parts. Longmont, Colorado, which is near Denver, America. That's where I previously worked. And then Europe, Raychag, about 45 minutes up from here. See the different moldings. So these are all plastic injection molding machines. We have, about 12 machines right now. Colorado has, I think they have more, maybe about 45. And then Florida has 18 in different sizes and categories. Furnaces, we have 3 large production furnaces and 1 small test furnace. They're going on in Colorado, I think has 10. Florida is a little different, because they have different open atmosphere furnaces. That's what we use. So molding, and you can see that's a look in the Colorado. You can see, this looks just like a plastic injection molding house. You can see all that. If you go to anybody who makes it, you'll see the lines of molding machines. We typically use Battenfelds, but we can look at other ones too. So we're going to see a few slides here about the details of molding tools. They just look like a big block of iron, but what is it? You have your A and your B staff. And how does it work? So you have your A side. That's the injection side, which has the hollow hold up. And then the B side, that's the motion hold up. That's the ejection where the part's pushed out. That's the terminology we use. And you can see the difference on that example. And you can see it in here. It's a vane. You can see it's got what's called an edge gate. The material just goes right into the side. And it's a 4-cavity mold. See the different aspects of the mold. We have the insert cavities, runners, the water channels to keep it cool, guide channels, and that's in the runners. These are the locks, and then the orange channels. B side is the ejection side, so where it gets pushed out. This is the whole ejection system. This is where the clamps go in, and then some of the watering of the mold we do hook it up to water, and they circulate water through the molds to keep it, otherwise we start melting the parts. Here's a different view of them together. There's a ring, there's the clamp ring, A and B side, and then you can see some of those. So this one is, sometimes you have parts with undercuts that a normal open and closed mold would rip it out. So we have to put in a slide in the mold, and you can see it, for example, if you need like a hole in there, and this is what makes it 3-dimensional. Not all, sometimes it works, but sometimes you need to put a slide in. So as that slide comes out, you can form holes, you can form undercuts. It makes it more complicated. So a good example is, you know, we have these helical teeth. We have 3 slides coming like that. If you just had it closing, you'd rip it out. And they can, usually they're mechanical, just a pin and a slide, but sometimes we actually have we have one right now with a hydraulic slide that pushes it in and pulls it out. So how does a molding machine work? What's going on with the molding machine? If you're not familiar with that, to make it really simple, the mold closes, so you think it's screwed forward, but what happens is the screw is going backwards. And as it's going backwards, you have your material in the hopper, and it loads the shot. So you can see it stop, material falls in by gravity, and then it says, okay, let's shoot it. And it pushes all the material forward. At the end of the screw in the barrel here, they what calls the check valve. It's a little ring, and that's where the ring is meeting the material and pushing it into the mold. And they do it at pressures up to, say it in PSI, up to 18,000 PSI. I don't know the bar, but you can see that it is a plastic injection mold. There's not many big differences between that and MIM. So what we're saying here is the gate. Where does the material go in? You can have different, how we take off the gates. You know, you have to have an edge gate where it just goes in the side and they cut it off. You can make it large, that helps it with the packing, but someone has to cut it off. And you have to have an operator sit there and cut it off. That's time, and it also creates defects. And then you can have something like a tunnel gate where it goes in there and cuts it off. So there's different ways of doing it. So you want to make a balance between the right gate for the part and then efficient and clean molding practices. If we have to have an operator cutting it, you know, they'll have a knife and they can create defects. Automation. So you want automation. But the reason is we generally do pick and place. The mold opens, comes in, picks it, puts it on a conveyor. And it's not just to reduce labor, but it's also to make the cycle time very consistent. If you're having mold that's 30 seconds, boom, open, put it on there, then you have less molding defects. You don't have things going wrong. There's less to go wrong. If it's person pulls it out, they cut it, and then I gotta look at it. This one's 30 seconds, this one's 35 seconds, this one's 25 seconds. You have more opportunity for defects in the mold. So we call it pick and place. That's the most basic, just puts it on a conveyor. Another one that actually, the robot comes in and actually puts it all on a tray, and then there's one that puts it on the tray and then indexes the trays and does the whole thing. So one person can run 4 molding machines. So this is an example of pick and place where we build the robots and then the heads, and then some of these heads we have actually, you hear about the 3D plastic printing. We actually 3D plastic print some of the parts to go in there, and it saves us a lot of time. That's an automated cell in the US, so the trays actually index up, go in there, robot stages it, pulls it back, pulls it down. Once it's set up right, it's very efficient. And there's another example where they actually run 4 machines by one person. Okay, so this one, this is more into the material side. This is the metal powder, and how do we characterize the metal powders. So there's 2 main ways. We have, first one you can see is water atomized, and the second one is gas atomized. We do a balance. Mainly we run water atomized powder. So the advantage of that is it's a little cheaper, and it creates rougher molecules that stick together. But the gas atomized is more expensive, but it molds better. It's spherical particles, you can pack it and do it better. Then you have to balance the price with the powder binders. So this slide is showing, when they do a gas atomized, is they're heating up a block of steel, and they're blowing gas either argon or nitrogen at high pressure across it, and that's creating a stream of the particles, and they classify the particle size. You can see in here, very spherical particles, but with the V's, they're much more rougher. And so there's advantages and disadvantages to both. The other one we do is what's called carbonyl iron powder, CIP powder. So your base material is iron powder, right? But it's not just make a melt, do a atomization, and you have your powder. It actually has to kind of go through this little chemical process where they get their iron particles, they combine it with carbon monoxide, they go through this, it has to decompose, but that's how they get the actual good powder deposition and distribution. So it's clean. If they just took the iron powder and atomized it, it would be very random. It would not be consistent. It would not be good for molding. We have some very specific particle sizes we like to look at. So you can see this comes from one of the powder vendors, Carpenter. And so that's how they're doing the powder size distribution. It's actually doing a swirling, and then the bigger particles are going to go to the outside, and that's how they measure it. So you can see the different particle sizes on the fraction there. We generally want to look at 20 micron average particle size is our metal powder. And for veins, we've actually gone to 10 microns. The smaller the powder, the better we can pack it. Might be a little bit more expensive, but in this case, it works for what we need. So they do, they give different grades of particle size that you can make there. Continue. So we use barcode system. Every powder gets a code. So when it comes into the lab, they have it tracked. So part of the automotive industry and everything is you need traceability back down to the raw powders that you have. So if there is any issue way in the field or anything, and they can give you the lot number that you sold to the customer. They said, okay, you did lot 4605. We can trace that all the way back down to the base powder and know that base powder was to specification. So this is one of the things in our lab. It's called a pycnometer. So if you're going in your lab and you're measuring your powder, one of the things we measure is powder density. We want to know when our powder is coming in that it's correct, that it's to the proper density. But how do you measure the density of a powder? You can't just weigh it and take the volume. It's not that simple. So what this does is it's a helium-driven machine. It takes a reference of a 10 cubic center ball and then the powder. And because they use helium, which is a very small particle, it can push through all the pores. And then you get the displacement of that volume, and then you have the weight of the powder versus the displacement, and you get a much more accurate version of your density. So we use that for powder densities, and also our little parts here. We measure these things in density with an Archimedes thing that's water displacement, but if it's very small and has holes, then it gets air in it, and you get a false reading. For a long time, we did something called tap density too. You have it in the lab, it's going ding, ding, ding for 1,000 times, and we've kind of gotten away from that. Pycnometer is better. These are, it says the binders, what is important? We have a different thing. It's clean. It's not hygroscopic. It has, the good polymer chains. We generally do to wax, which is low temperature melting, and polypropylene. And by low temperature, we mean about 250 degrees C up to 600 for the polypropylene as it's going through the sintering cycle. So what happens here when we go to make a part? When when we're making the thing. So you can see the gentleman there, he actually has the barcodes weren't there just for the tracking. They're also, the machine will tell you, it says, okay, beep, please add 60 kilograms of this power, 60,000 grams. And then the machine will actively weigh it up to that thing. And then it'll only let you go to the next step once you weighed it to the correct weight. And then what he's doing here is, you can see the powder gets put into the canister here for 60. But if you did that, and then you added the binders afterwards, and you make a mistake, you'd have to throw the whole thing away. So what he's doing here is, once you've added the powder and put it in here, you don't have to scrap an entire batch. Because 60 kilograms of material actually can be a lot of money, especially on some of the stainless parts. And then after it's done, it goes through a dry mix. It's about 30 minutes of a tumble. Then here we have the what we call our Ross mixer. It's a batch mixer. So it has an oil heating jacket, and it goes for about 40 minutes. And that's kind of, you know, like we say, this is where you're baking the cake. And it has paddle mixers. And then it goes on, and then it's measured by the amp draw of the motor. So as it gets hotter, it's creating more viscosity, and it's pulling more energy off the motor. And then it's pulling more, and then once it's broken down, you'll see it'll drop off, and that's when we know the material's up. But that's controlled by the computer. They used to have some guy look at it with a flashlight, but that's not controlled. So these are some pictures of the Gillemot house and compounding here in our plant in Hungary. So we have the two main ones I showed you was the batch mixer, the Ross, and then for all of our turbocharger vanes, we use what's called an extruder, a hex mixer. It's a continuous mixer, but we don't introduce other materials to it for any fear of contamination. So you can see after it's made, it goes into the grinders, and it comes out granulized. And we can pass that around, but that's what it looks like. And then one of the things that makes it economic is in plastics, you have the runner, and the runner gets thrown away. But for MIM, we take that runner, and then it gets reground and mixed with the original material, and then you're not throwing any material away. And that becomes it's very important for economics. And it's also very important for when you're using more expensive materials. In aerospace or something like that, when they have real high nickel content parts, you don't want to be scrapping material. So when we regrind it, we use all the material. Nothing's going to the trash. And then this slide shows you just normal pignometer density for 440 stainless steel, as I explained on the pick. We also use a rheometer to get the viscosity. So we want to check each batch for viscosity. So if there was a contamination of the batch, you would have a different viscosity. We could stop the batch right there. You don't want a contaminated batch going through, and then even if it might look the same and pass through your checks, but if it gets to the customer, that would be really bad, and they can't use the parts. So this is an additional check we have to make sure that the viscosities are correct of the made feed batch. So this is the binders and debinding and the symmetry. So the main ways of doing the debinding, you have diffusion and vacuum and wicking and bedding. We use the solvent bath. It's very simple. It just goes into the bath. It sits there for 4 hours. A little agitation, a little elevated temperature, something like 70 degrees C, but that's it. But that extracts most of the binder. Most MIM companies use this. If you have a really, really small part, you can use a thermal debind, blowing hot air on it, but only if it's a really thin part, and that can get out. So what this slide is showing here, this is a molded part, we call our green part, okay? So the orange, that's the metal powder. And then the green here, that's the debind line. After it goes through the debind, it now becomes, you've extracted most of that. You can see a little bit remaining, but it's now a very porous material. It becomes flexible or breakable. You've lost about 3 or 4% total weight, and hopefully about 90% of the total binder extraction. And then you can see that's what we call it, the loss of extractable binder. We want more than 90% gone. So it's not going to come out in the sintering furnace. It's going to come out in the debind phase. We don't actually need it, but if we didn't do that, we'd have a really, really long ramp in the sintering. And because the sintering cycles are expensive, they use a lot of electricity. And everyone knows the electricity prices have gone up recently. So we want to keep that to a minimum. So this just shows, we used to use trichloroethylene. That got banned by the European Union. So now we use perchloroethylene. In America, they use 1-propylbromide. You can see some of the pictures over there. And a few different pictures of what they do. They do have, you have the full drying process and all that. It's not the greatest picture, but this is the picture of the debind unit in our plant. We have 2 of them, but it is enclosed. It's on the side of the plant. We actually have positive pressure blowing it out, air out the side in case there's any solvent. It's a safety issue. That's how Florida does it a little differently, and you can see on the left here, that's where they do the thermal debind. But it's because they use such small, thin parts for the medical. You can have a little plastic bag and it can be worth 40,000 euros. And so they have a table of people getting under microscopes and looking at it on the brown parts and making sure they're okay, because they have to go restage the whole thing. So you can see the brown parts will sit on the special trays. After they're debind, some of the waxes kind of actually can stick to the ceramic trays. And because it's going to be floating in a liquid, and then it's going to stick there. So sometimes we have to actually move it. We don't do that very much in RHAG, but sometimes we did do that, and we have to make sure it's straight. So you can see this is a picture of a standard vacuum sintering furnace. So our sintering furnaces, we have graphite fixtures because it has to withstand the temperatures going up to 1,300 degrees centigrade. And so you have to have material that withstands that, but doesn't melt. So there's graphite, there's tungsten, there's molybdenum, but the graphite is mainly used more as obviously it's going to be a little less expensive. And then if we need to replace something, it's there. And it's easier, much easier to machine, the fixtures and what we call the furniture. And you can see some of the heater elements over here, and then some on the door. That's going to be the molybdenum and the tungsten. So you can see this. This is the graphite fixture up here. So we define our tractor size by 1 vertical column. So 15 down, 3 across. So it's 45 trays, and how many pieces we can get on a tray. That defines the number of pieces per lot. You can see them loading it in there. So, like I said, between 24 to 28 hours is the total cycle time. But it is one of the most cost-driven parts of the process because of the electrical consumption. You see the different pictures. So this is in the United States. This is one in Colorado. The one is a little bit bigger. And there's a top view of it. You have a lot of, it's a vacuum, so you have to have a roughing pump and a fine pump, and you have to get it down to almost zero vacuum before it's going to work and it can come on. So what's happening up there? That's what we call our sintering ramp. So once the door is closed, it starts pumping down the vacuum, and then the temperature starts going up a pretty good degree per amp, like 2 or 3 degrees centigrade, and then it'll do a hole for an hour to let the temperature soak in through the whole fixture, and then it'll go up to the next level, usually about 600 degrees. So by the time it hits 600, almost all the binder is reactive. So in this first phase, the binder is slowly coming out, and we have a trap, and it gets caught in that trap. So by the time it hits 600 degrees, it's pretty much all metal, but the elevated temperatures are keeping it shape. But it hasn't started shrinking yet. So you can see the ramp up to those things to the top. You have a quicker ramp up to a little bit before you hit the peak temperature, maybe 1,200, and then it'll do a 3-hour hold there. And that's to let it all soak in all over the fixture for all the parts. Because we actually get 60,000 vanes into one, that's a lot. But that temperature has to soak into all of the vanes to make sure they're all done correctly. It could be quicker, but we need to make sure that everything is done right. And then at the end of that, we have what's called the static cool. Electricity cuts off, it just cools by static, because it's still very hot at that point. And then at either 700, 900 degrees, one of the either argon or nitrogen turns on, and it brings it down. So that's a sintering cycle. But at the top there, on that thing, that's where the shrink and the densification is happening. At that 1,000, that's where it's going. Once it starts that phase, it's still at the 20% bigger, but at the elevated temperatures, that's when it's fusing together. All that porosity you see is now getting eliminated through the higher temperature. We do have a special furnace, also in Reykjavik, called our element furnace. It's a little smaller, but you can see it's cleaner. There's no graphite. This is all tungsten and moly, and it can go up to about 200 degrees higher. So you can work with some more exotic materials like titanium, higher nickel. We did an Invar Kovar development, cobalt, nickel iron, and the other one was just nickel iron. So in Florida, we don't do that in Reykjavik or Colorado, but in Florida they have what's called an atmosphere sintering. They'll use either hydrogen thing. You said, okay, I'm having a hydrogen thing. So you want to be careful of it because it could, it could explode. But so they have an afterburner on the top, so it's not creating any pressure. But what it does do is it gives you a uniform atmosphere for it to sinter. It's not just a vacuum. And actually you get much better results out of that. But you have to go to the trouble of having a hydrogen atmosphere. And they have to have everybody stack this. So it's a little bit more labor intensive. This is what's known as a continuous furnace. So you can only run one cycle on it. It literally takes it a week to clean. So the tray will go through kind of a channel, a heated channel, and all the way up and out. But it has an atmosphere, and you can see it's got an afterburner to burn off anything from there. But the advantage is if you're running one material continuously, then it makes sense. But like us, we have the flexibility to run the vane material, then the next day we can run an iron or a stainless material. And then it's driven by the number of pieces in economics. But we found that the batch furnaces work best for us. So getting back to that slide, and you can see this is kind of where the MIM is coming from. You have the green part, where you have the metal powder and the binder. Binder's removed here. But then you have, so this is where the shrinks happen. You can see how much it gets down. And we want to get densities up to 96 to 98% dense. Versus wrought or fully cast, which is 100%. So we actually get pretty close. Powder metallurgy, they get about 90%, so it doesn't have the strength. If it's a 2D part, it's okay. But on a 3D part like us, you want to get closer to that 100%. So you can see the size difference. And also, a lot of people, if they don't seen it before, you can really see the you can really see the difference between the size of the parts. Pass that around. So we like to call this our shrink factor, 1.15 to 1.25. Biggest question we get is how do we control the dimensions? Are they all to the same? Are they all to the same dimension? Is it a uniform shrink? So in theory, yes. But within what tolerance? And what tolerance does the customer want on the print? So they say, I want all these tolerances. So we generally say plus or minus 50 microns on any dimension. From 10, say 10 millimeters, you get plus or minus 50 microns. Now, or a 0.5%. Now, if you just do the straight math and you have 5 millimeter, that's plus or minus 25 micron. But we don't want to do that because then it starts getting too tight. So we go down to plus or minus 50. So the answer to that question is what is your uniform shrink? We'll say that down to plus or minus 50 microns depending on the geometry of the part. If you have a real thick part like that, that's stable, you can say, yeah, that's what it's going to be. But if you have something with a cylinder with a long hole in it, as it centers, it's going to distort a little bit more. So it's going to be not so much that plus or minus 50. You're going to need a little bit more tolerance. It's all on what the customer needs as well for their application. So after the centering, we measure the density through the Archimedes principle or the pignometry, and we always measure the carbon content. It's steel, you need another percentage of carbon. There's stated in the ISO or the metal powder industry spec. Usually something like, it's about 0.3%, and the stainless steel, this, max 0.07, usually about 0.04. So actually a pretty low carbon. Hardness, so any heat treatment place, or if you have a hardness measurement in your lab, you do HRC, HRA, then micro hardnesses, almost every part has some type of measure like that. So one of the other things is we've talked about the technology, but there's also the quality side. We are a manufacturer and we have to put out parts to a specification. So how do we control that and what is the quality? I'll go through this a little quicker, but it's very important. On-time delivery, we don't want scrap, we want to be below 5.5% scrap, things of that nature. The customers will wait a little bit. If they want their parts on time, they order it, they want their parts. So you have to deliver it on time, you have to deliver it to the price, and if you release parts to the customer that are not acceptable, that's part of the quality system. So these are the different quality standards, the ISO, the TS, and we get audited every year. Mainly we stick with the automotive, Florida does the medical, and Colorado does the aerospace. This is how do we do tracking and traceability. Really, we go from the raw material lot, we have data trace and a priority system, a new ERP system, but you have to trace everything down to raw material. That's the most important. You can't lose it, or if you lose traceability, you have to throw it away. So you can, this is kind of a flow chart seeing that, powder 1, powder 2, it goes to the compounding, low down beyond in the sintering, but you have to have the traceability. I'll go through these a little quicker. We have a tracker with a barcode, so every lot has a tracker that goes into the system. So these are the formula. You can see all the different binders and all the different powders. Each compound gets a code, and each lot of material calls an IM, internal melt code. Each lot of material that we make, that's its lot, that's what it was made from. Different color coding on it, and then you also have things like furnace run, what center cycle it was, date. Gotta have traceability for everything. What was the sintering cycle? Okay, I'll go through these a little bit quicker, but all parts have defects. You're going to have something, but you have to work with the customer as to what is acceptable. Just because a defect doesn't mean it's a reject. So you're going to have things like that. So when we look at machining, critical surfaces, is it cosmetic, is it not? So we say this is the acceptable MIM defects, the flash, blisters, debris. Some are acceptable, some are not. You have to have a criteria from your customer. So I'm gonna go through all the charts there. How does it measure and what's going on? So when we start a part, we go through all these criteria, say this is allowed, this is not. One thing is for example, you do have cracks in material sometimes, not all the time, but you never want to get in an argument with your customer, what's a good crack and what's a bad crack, because it's usually bad. That's the one you don't want. So if we have a not acceptable part and it's caught in the system, and we have an MRR report, material reject, and the parts are put on hold and has to have a disposition. We inspect all our documents, it goes to the data trace or SharePoint, and now our ERP system. Work instructions, they all have to be traced, revision, and into a system, and that's part of it. Calibration, so we can't just get out a micrometer or a caliper thing, or even a CMM. We have to have someone come in and calibrate it so we know every year that it's actually doing it correctly, and it's stamped and it's gone. And that does get audited as. These are our suppliers. So our biggest one is raw materials, machines, tooling, and then what we call OSP, which is usually heat treatment, machining, and plating. Almost all the iron parts get heat treated and plated. The stainless steels, sometimes they do, sometimes they don't. We want to get shipping documents. We always have to give it a certificate of conformance that it met the carbon, it met the density, and it met the dimensions. So as I said before, a defect is not necessarily a reject. So that's when you work with your customer. If you get something and it's a little sinky, is that a defect? Not necessarily. Is it a reject? That's what the criteria you have to put forward. This slide is a little busy, but it shows you the different ones. Flash, burrs, missing material, distortion, cracks. It's kind of busy, so I'll keep going. There's some different ones. Cold flow, broken, some different ones there. Blisters and flow lines. It's a molding process. You're trying to push material and you're going to get things that look like spider lines, different temperatures that go in there. If the mold setup technicians do it correctly and you look at the parts when it goes on, you can say this is okay, but oh, this is a cosmetic surface, not okay. So you can see some of the different flash. You can see it right away on the green part. They're acceptable or not. Usually not. Missing material. What is that? Oh, that's a stress crack. This is our a gate that wasn't taken off. There's a piece of flash. These are some of the different defects. Cracks, some burn marks. This is a really good example of the sink. If you get a thick section, it goes in like that. So, might not be acceptable here, but it's acceptable here. You have to work on it. Missing material on a thick section, it'll sink in and then it may crack. So that's generally not acceptable. Cold flow, so you'll have a different temperature in the same shot, and it'll come out and it'll look like little lines. Sometimes it's okay, sometimes it's not okay. You have to see how it works. Any damage, they're usually not okay. Nobody wants to damage a ripped part. And you have to catch that at the molding. Stress lines, usually it's plastic. If you've ever taken a piece of plastic and just pulled it apart, you'll see a white line come out of it. You're stressing the plastic. You see that in your plastics. Well, same thing here. And usually inside a cylinder hole, you get a white line that comes out. And that'll turn into a crack. And so if we see that, something's going on in the tooling that's stressing and pulling them apart. And we don't want that. Here's some more examples of flow lines, how the material's coming out. Blisters. Generally, blisters are not acceptable. If the material's too hot, the gas can't escape from the part. And that's taken care of. We have a requirements review with the customer, what's acceptable, what's not. Most of those defects aren't acceptable, but you have to work with them. These are, I'll go through some of these. So we have the different things like coining, trays, heat treatments. So they use a cell here for inspections. We have a lot of parts that get coined. So the MIM, it'll bring it into a net shape, but sometimes you need to press it to the right size. And that's much faster and quicker than machining it. But it only gives you a certain tolerance. If you have a really tight tolerance, then you do have to machine it. So this is different examples of coining, spreader. This is a collet coiner. They call it the sheet lapo, called the flat plate sandwich coiner with a different gauging. Different types of press, the hydraulic presses, and then one pneumatic press. This is some of the ways they do it in Florida. This is an interesting one. Is sometimes if you're looking for a crack, you can't detect it. It's really hard. No one wants to do X-rays. It's really expensive unless they pay for it. So you can drop it on a little bell, and it'll make a different acoustic signature, and it'll kick out the bad part. It's a quick way of doing it. Almost all of our parts get tumbled. When they come out of the sintering furnace, they're silver metal, but they're still kind of sharp. You know, if you handle it, you can scrape your hands. So we generally tumble everything. That just smooths it out. It gets rid of any residue, and it makes it better for the customer to handle. And also, almost sort of the sandblasters. So you can use a basket blaster that cleans it up without all the soap and the residue from the tumbling. That's Florida's heat treatment. So one other big thing is we have CNC machining. So we have 3 CNC machines plus our grind cell. So if you need something with tight tolerances, like I said, below plus or minus 50, if you need to drill something or even get to plus or minus 15 microns, that's when we send it to the CNC cell. But we have to make sure that it's set up, it has the right fixtures, it's in the process, it's accounted for in the cost. So this one is, we have our grind cell. And that's really important for all our turbochargers. So this is a turbocharger vane. You know, if you have a Volkswagen or Mercedes or that, they use the variable geometry turbochargers. What that does is it gets rid of turbo lag. You don't feel it anymore. But these diameters are done to plus or minus 7 microns, really tight tolerances to work on that. And this material goes up to 800 degrees centigrade, sometimes 1,000. So that's what these machines are for. And we have 16 of the old type, and we now have 5 of new, more efficient machines. But we're pushing through 8 to 10 million of these a year with this grind. So it's really important. But we don't get that in MIM. We have to, this is an example where you have to have this grinding to have these really tight dimensions at this really high volume. But that's when it goes into their automotive world. And this is 310 stainless steel called HK30. It's relatively soft actually, but it withstands high temperatures. And that's what it's designed for into the inlet section of our turbocharger. So you can see some of the areas that are getting machined, incomplete holes, some of the reamings there. More machining. This is like 2 through hole example. You machine one, so you have to have it both come in. A lot of times they have a fork with 2 holes. Different reamings and locations and machinings there. Tap holes, blind holes, some of the different machinings. Slot, profile, but you know we're machining that profile as the main one. Either grind a face or drill a hole, but it's the tight tolerances where we get it to us. We'll check out some robotic vision systems if we need to do sorting. You can see the different sortings they have there. If we have a high enough volume, you know, if you're getting into the hundreds of thousands or the millions of parts, then you can justify buying Corning machining cells. You can say, all right, I have this amount of sales per year, it's going to get bigger, I want to make it efficient, then we can invest in some machines. And that's what, some of this does, is they're Corning machining cells. So we have some of these. What else can we do? Machining, heat treat, almost everything gets heat treated. Electro polish, black oxide is a big one. Passivation, We have one called QPQ here in Budapest. It's like kind of a hard blacking coating, nitriding. So go a little faster. So now for your materials. What materials do we use? So our main materials is for stainless 17.4 for the 400 series, martensites, and then austenites. Like I said, our vane is 310 stainless steel. It's called HK30, that's a trade name, but it's 310. We also have 316 and 304. This little part here, this is 316. So it comes out of the furnace just the way they want it. And then some of these parts, 17.4, that's one of our biggest uses for stainless steel. It's a little bit more expensive, but sometimes you don't have to heat treat it. It's corrosion resistant, and it can work. You can sometimes bypass those secondary processes. And then on the non-stainless side, we generally do 2% nickel iron, sometimes 8%. When it's 4140, that has almost about 0.5% of nickel in it. So you can see that, you know, a lot of the firearms do that. So that's this side. You can say, you know, I said the 4140, 430L, the magnetic. We did one for diesel engines of an armature and silicon iron. That goes into armatures, so you can have a real specific magnetic field. Rusts if you look at it funny, but it's good for that application. And then on this right-hand column, you can see some of the different aerospace materials. We do get a lot of interest in the Inconel 713L, nitronic and nimonic 90s, but here's the thing, those are very expensive. They're 6 times more expensive than the HK30s. They can resist higher temperatures, up to 1,000 to 1,100 degrees centigrade for more gas turbos and something higher. But, and here's the big but, and this is what we work with the turbocharger manufacturers on, is it's a lot more expensive because of the nickel content. So they're trying to find that one that's in between that works. And then some of these Hanes and Inconels and titaniums, those go into the aerospace. Those are really specialized nickel, high nickel content materials. So the next slide I'll show you real quick is, big question, other question besides the dimensions is, how does the MIM material compare against raw, straight cast? And you can see on tensile strength and investment cast, here the MIM here on HK30 is either the same or better on tensile strength. So we like to show our customers that it's, because they just don't know it, they are not familiar with it. The turbocharger manufacturer, Garrett, it took them 5-6 years to get comfortable that the MIM material is going to perform the same as a wrought material, as a cast material. Then they can get the cost advantage of the MIM. So the same thing happens here with nimonic 90. That's another high exotic material. Titanium 6.4. Really difficult to mold, because if you guys ever work that stuff, it's expensive, and it's an oxygen grabber. You have to have something taking out the oxygen, otherwise it's brittle. Inconel 718, another big one with nickel. Then the F75 cobalt chrome is used for implants. You can use titanium, very difficult. But if you can't use that, you can use the one that's cobalt chrome for implants, and they do some of that. Knee surgeries, as we all get older, knees, hips, that's the material that they make it out of. So what drives the cost? As the parts get bigger, the material becomes a bigger factor. When it's a small part, 1 or 2 grams up to 10 grams, the material cost of the part's not so much, but it goes up exponentially with that on the material in this area. You can see the different costs. I alluded to that. The stainlesses are going to be a little bit more than the irons, and of course the high nickels are going to be 6-7 times more than that. And then this slide I was thought a little bit difficult to understand, but what it does is, one of the things we talked about is, how does MIM compare to other technologies? So if you look here, so versus casting. Casting is investment casting. They're better for bigger parts. and other materials. The casting is a rougher surface, and they essentially have to make a new mold for every time they do it. Whereas us, we have a steel mold and it comes out and it's the same thing every time. So bigger parts is better for casting, smaller parts is better for MIM. PM, powder metallurgy, if you think of gears, it's two-dimensional, press and sinter. Cheaper, but only 90% dense, not as strong. Machining. So machining is better for the lower volumes. If you want to make 500 pieces, make it. Have it machined, and then they do it, they're done in 2 weeks, here you go. But it's more expensive. But as soon as you get higher volumes, you want 1,000 pieces, you want 5,000, you want 10,000, that's where the MIM starts becoming more economically advantageous. And then stamping, if it's just a thin piece of metal that gets stamped, we'll tell the customer, no, this is a stamping, it's not MIM. Die casting, if we compete against aluminum or zinc, other big question is, hey, do you guys do aluminum? This would be a great part. When we're talking to the rock climbing people and carabiners, they do all these parts in aluminum, but very few in steel because of the weight. But unfortunately, aluminum, due to the melting temperature, doesn't work in the MIM injection mold. And then screw machine, if you have a little part, it's great for all the other features, but the screw machines, they put in a rod of steel, they make it, they can pump out hundreds of thousands of parts in an hour. But in 2 dimensions, not 3. So this is the NPD formula. The biggest thing here, and I'm trying to keep on time, is the requirements review. So when we got a new part, we sit down, we've given them the print, we've given them the rough pricing, but we sit down and say, what are your requirements? Do you need to microscope everything? Do you need to x-ray things? Those are all things, 100%. And we ask them very detailed. What measurement frequency do you do? Do you use a micrometer 100%? What are your critical dimensions? All of those questions that get answered, and then we can get a real picture of what is required for the part and more accurate pricing. And there's just more slides on that. We have to have the 3D model so we know what's going on with the part. We can make it tooling. This is kind of busy, but this is all the little steps of going through new product development flowchart. Into that. And also, these are a little bit simpler. You get the requirement, the customer gives you the PO, the requirements review, and then we kick off the tooling. We have to make a mold. Then you make the mold for 8 to 10 weeks, and then comes the fun part where you have to start making parts, incinerating them, and checking the dimensions and making sure you're getting things to the print. And if not, you have to work with the customer on what you're going to do to get acceptable parts. So these are the 3 quality criteria. We get the tooling PO, then we have an alignment meeting, and then we get it running full production. So what we say is the NPD part, it has not been approved. Second part, yellow, it's been approved, but still not ready for manufacturing. The engineering has to look after it and chase it. And then once it's done, it has good efficiency, it's profitable, has minimal scrap, then you can release it. You can throw it over the wall, and then the manufacturing can make it to acceptable. Different teams, we have gated processes for each step. I'll try to keep going here. Dedicated teams, program managers, project engineers. We now have a couple new metallurgical engineers. That's really helpful. Does this material fit? How we're going to do it? What's going to work on it? Logistics and quality. And then the big one seems obvious, but communicating with your customers. It's, hey, the mold's going to think. And one thing I learned over a number of years is if you have an issue, pick up a phone and call them, even if it's not good news. No one likes to say bad news, but if you do that, it makes things much smoother. So the good communication customer, even if things aren't going well, that helps smooth it out and you can come up with a plan. If they're not feeling communicated with, then they're not going to be happy. These are the different features in MIM design, threads, radiuses, different things like that. How we do identifications, you can see cavity numbers, lines, all little different ways we put that in the mold. Ejector pins, you can see, we have to push it out of the mold somehow, but we have to have that approved by the customer. Threads, I'm in the middle of doing threads for a new customer right now, and they're difficult. So if we do internal threads, we're going to machine it, because in MIM, you have to have an auto unscrewing mechanism, and that makes it difficult. It distorts in centering, it has gravity. We'll just have it machined, we'll make sure the cost is there, and then they'll be happy. External threads, only if it's a really thick thread can it work, and you can see a flat there, because when the mold closes, you can distort the threads. Parting lines, where does the mold come together? So you can see you're always going to have a line. Mold comes together, you're going to have a line. Is it a problem? Is it not a problem? You have to talk to them about it. The runner, we call it Angus, goes from the injection point of the mold of the machine, runs out, and then gets put into the mold itself. So you have the different cavities and the runner. Sometimes they're in the back of the plate, sometimes they're in the front of the plate. Depends on the design you want, like a 2-plate versus a 3-plate. These are the gate, the Bayonne point. You can see different locations and different sizes. You can have a tunnel. Mainly we have tunnel gates or edge gates. Tunnel gates go straight into it. When you open the mold, it gets sheared off, so that's an advantage. The disadvantage is it can only be a certain size. So if you have a larger part like this, you can't maximize it. You want to pack it out, so you want to have a large gate, so you're not restricting the flow of the material. When you do that, you have to cut off the gate. So you have to make one trade-off with the other. You can see the different drop gates. A 3-plate mold means the runner is contained within the mold, and when the mold opens, it automatically drops, which is nice for production, but it makes for a more complicated tool, and it makes for a much bigger run, which means you may be maybe not wasting material, but you have to grind more material. It's here. So just like this is a little bit larger vein, goes in pickup trucks. You can see it coming into the side there, and then they have to cut it off and do it, and cut it with a knife. But that can lead to defects, and you don't want to do that. Call this the diaphragm gate, or you say Zuhan. When you have a cylinder and you want it round, you want it coming down as a flow, and that helps it keep it round. And so that's one advantage, depending on the design. However, that usually needs to be machined out. So if the part's already getting machined for a hole, that's great. You don't have to add a machining step. But if not, then you do have to add that stuff if it's justified. So let's get a little bit of the MIM design. You can see that there's all different kinds of parts here. This is a wine stop. This is a blade holder. This is an electronics box. Another blade holder. This was a blade holder, but a combination of 3 different parts, and this was a turbocharger. So one of the interesting things about our technology is you get a lot of different industries. You're not buttonholed into just one industry. So from a design point, when you're an engineer, right, you're looking, how do I make this? What factors can I look at? Okay? So these are the things, wall thickness. We have some different wall thickness here. We want uniform wall thicknesses for molding. We don't want big, I call it dead weight material, or big thick sections where it has to be uniform. It makes for a bad mold. More molding defects, sinks. So sometimes, and then you're just wasting material. You're having material that you're driving up cost for the customer, and you don't want it. So if you can core it out, we call it coring, you're removing material and having consistent weight. You can see the walls right here, the thickness of the weight, 0.1, that little fuel injector part, and then we have a part we're working on right now. We said 250 grams. We're actually working on one 320. But after a lot of trials, it's starting to come out without cracks and without distortion. It just takes some work. And then this one is the big one as we look at what are the dimensions that you can count on and you can get. Plus or minus a 0.5%, that's what we see. But you have to look at each individual part and how the centering and gravity is going to work for it. So a typical plus or minus half, maybe a thing, all depends on the dimension. If it's a thick, nice dimension, it's going to keep it. You can do a little bit better than that. But if it's a long, thin one, it's going to distort a little bit more. You have to look at each part individually. Weight, degrees on angles, typically plus or minus a couple degrees. We can go to plus or minus a 0.5 degree if we want to. Then this slide shows gating locations and transition points. So you're having material flow through a mold. So you don't want it going on sharp angles. It's got to go around it, and it's not going to flow properly. So you want it going on a curve or a radius, transitions. And as I said, coring. You don't want a big, thick part. So these parts are really good examples of it. If we had this vein full, it would weigh like 50 grams. Now it weighs 17. We don't need, and it's, as you can see, it's all uniform walls. And then with the center wall in there. So you get the strength of this with the ribs, but you don't have all that dead weight in there. You can pack the part without having big sinks or useless material. You want to keep that, you want to keep the weight down. And then, so MIM friendly. If it can sit on a tray, if it can sit on a flat tray, let's see if I have an example here. I don't. So if it can sit on a flat tray and center, it's supporting. So when it's up at temperature, it's almost liquid. So you're sitting there with gravity. So think of it like this, guys, here. It's got this arm that's hanging out. And then if you're up at 1,200 degrees, it's going to come down. Gravity acts on it because it's almost liquid. So we have to make ceramic blocks and trays that's supporting. Each part is different. Sometimes we need it, sometimes we don't. But we have to design specific trays for this to hold it up like that, to make sure it's not falling down and it's not distorting. So you can see some different pictures like that. Forks, sinks, drags, different trays, different staging. We have our trays on ceramics. 2D versus 3D. So this is where you get into your design, what makes it MIM. Press and center, 2D. Do it. It's cheaper, but if you can get a more complicated part, combine 2D, and it becomes MIM. You can see the different, get more holes in it, flats, things like that. This is an example of like, that would start off as stamping, and then you start adding some things, and then it becomes MIM. Combining parts, you can see the, press and center, just a slate slab part, but like this guy, you can combine a few parts. A helical gear and a cylinder in one mold, and you get it, like 3 parts right there. This saw blade part was a good example of that. Really complicated tool, but once it's done, it goes, and we had no coining, no machining, just a heat treat and a plating, and it's done. You can see some of the different case studies. We had electronics, fiber optics, cell phones. Let's see here. Try and get a good. So the fiber optic parts, they get electro polish, things like that. Automotive, like I said, turbocharger vanes, impellers. You get all kinds of different applications. Saw blades, you can go there, saw blade holders. Medical, I'll show you this afterwards. All the medical parts are really small, but really complicated. So think, you know, as you're an engineer, how am I going to make this? That's the big question. How do I make this? And this is one of the processes for how do you do that. Firearms, we have a small percentage of firearms, but they are there. And then in aerospace, the thing with aerospace is we don't waste materials. So if the material is really expensive, the MIM can take a $100 vein like that and turn it into a $30 vein, just with MIM, including x-rays, including 100% inspection and things like that. This part right here goes into it's really simple, but it goes into a Boeing 777 brake system. But why is it MIM? Because it was using 42% nickel. And that's where the MIM comes in, and you don't waste material. So it's a real simple shape with this arc, you just bend it. But if you're bending or machining, and you're wasting material, but here it's not, and you can keep that. A real small hearing aid, a real thin wall box you can go into. Medical parts, you can have a hollow handle, and then this little fuel injector I talked about. So this is one of our best examples of MIMs. You have to make millions of these a year, 440 stainless steel. So if someone says, how do you make this? What technology you can use to make this? And then MIM is really the only answer you have to make it economically. And even theoretically, you can't machine it, you can't cast it, not at that price, not at that money. So we always consider this a really good example of where MIM is the best fit technology. That was another auto industry part, 3 parts together, one for your column shifters. And then these are just some of the different MIM versus other technologies where it fits, annual production versus complexity, things like that. What design things do we have? Size, up to 0.1, up to 250, vast differences in size. But generally we want to be smaller parts and detailed. Wall thicknesses, degrees. So, thank you very much. I appreciate your time.